Section: Introduction. We're going to talk about large language models, LLMs, which are becoming increasingly popular due to their ability to perform a variety of language tasks and generate coherent, lengthy text. As these models are used more and more in situations where they interact with humans, it's beneficial to have some control over them. For instance, we might want the text they generate to be unbiased, non-toxic, and helpful. We might also want the text to have specific properties, like a positive sentiment or a certain writing style. However, LLMs that are trained on large, unfiltered text datasets often don't produce text with these desired attributes. This is why we need techniques that allow us to control the text generation process. One simple way to control the text generated by an LLM is to train it on data that has the properties we want. Alternatively, we can train the LLM with control codes that indicate the characteristics of the text, which can then be used to guide the LLM to generate content with those characteristics. If we have them, we can use human annotated preferences to train a reward model, which can then be used to train a language model using reinforcement learning. However, these methods have their drawbacks. They can reduce performance on text that is different from the training data, and the work done to control one language model can't be reused for another. Additionally, the cost of additional training can be very high, especially for very large models. To avoid these issues, we can modify the decoding procedure used to generate text from a language model. For example, weighted decoding changes the probabilities assigned to each token during decoding using an auxiliary model. Most weighted decoding methods use a separate reward model to get a probability for an attribute, and then use Bayes' rule to construct text probabilities that are conditional on a class. Weighted decoding only needs the next step probabilities output by a language model, doesn't require expensive training, and is often modular, meaning a single reward model can be reused with many language models. Despite these benefits, weighted decoding can significantly increase the cost of decoding and often doesn't perform as well as methods that involve further training. In this paper, we introduce Reward-Augmented Decoding, RAD, a weighted decoding method that guides text generation based on the reward given by a reward model specific to an attribute. RAD uses a unidirectional reward model trained to output a reward that represents how well a given sequence aligns with a desired attribute. The unidirectionality of the reward model allows us to store intermediate activations as the sequence is generated, which greatly reduces computational costs. During decoding, the tokens with the highest probabilities are rescaled according to the reward model, making it more likely that tokens that better reflect the desired attribute will be chosen as the next generated token. We tested RAD's effectiveness on standard detoxification and sentiment controlled generation tasks, and found that it guides text generation towards a desired attribute without sacrificing much diversity and fluency. We found that RAD performs better than other weighted decoding methods and achieves results comparable to methods that involve additional training. Reward-augmented decoding works by feeding intermediate candidate sequences into a reward model that evaluates their alignment with a desired attribute. Then, at each decoding step, RAD uses the predicted reward of each candidate sequence to modify the token probabilities output by the language model. We use a unidirectional reward model, specifically a transformer decoder with causal masking, to compute rewards for candidate tokens at each generation time step. In a unidirectional model with causal masking, previously computed representations remain unchanged when new tokens are added, so at each generation time step the reward model only needs to compute the representation of the newly added token. This reduces computational costs. In this work, the reward model is a modified pre-trained decoder-only transformer, GPT-2 small in all of our experiments, fine-tuned on text annotated with the amount of the target attribute present. We use a cumulative squared error loss that takes a weighted mean of each prefix's loss. The cumulative loss encourages the reward model to output the correct reward for every prefix of the text sequence in order to capture both current and future alignment of a candidate sequence with the desired attribute. Section summary. Large language models, LLMs, are widely used for generating text, but controlling the properties of the generated text can be challenging. Additional training or control codes can be used to condition the text generation, but these methods have limitations and can be expensive. An alternative approach is weighted decoding, which modifies the probabilities assigned to each token during decoding using an auxiliary reward model. In this paper, the authors propose a new method called Reward-Augmented Decoding, RAD, that efficiently steers text generation based on the reward returned by an attribute-specific reward model. RAD outperforms other weighted decoding methods and achieves comparable results to methods involving additional training. Section: Weighted Decoding. Let's delve into the concept of weighted decoding. The RAD method uses a technique called top 7 sampling and adjusts the probabilities of the tokens with the highest probabilities based on each candidate's reward score. To put it simply, at a specific point in time, the system recalculates the probabilities of the top 7 tokens by considering their reward values. This process effectively adjusts the probabilities of these tokens according to their relative reward difference. This is a key part of the decoding process in RAD. Now, let's look at how RAD performs in 2 standard scenarios: preventing the generation of harmful text by language models, and controlling the sentiment of the text generated. We compare RAD's performance with several other methods, including the base language model without any interventions, methods that use signals from auxiliary language models to modify probabilities, and methods that adjust probabilities based on the risk of generating harmful text. We also consider methods that further train the model on data with the desired properties, and methods that perform fine-tuning on attribute-annotated data. In our first experiment, we use RAD to remove harmful content from text generated by GPT-2 Large. We use a reward model that has been fine-tuned on 2 million human annotated comments with continuous labels between 0 and 1. We then evaluate RAD's performance with different values used for sampling and adjusting weighted decoding. We measure the performance of RAD using several metrics. For each prompt, we generate 25 continuations, each containing up to 20 new tokens. We calculate the average maximum toxicity score and the probability that at least 1 out of 25 continuations is harmful. We also measure the diversity of the text and its fluency. Ideally, a good method should reduce toxicity while maintaining fluency and diversity. Our results show that RAD strikes a good balance between reducing toxicity and maintaining fluency, without significantly sacrificing diversity. It performs better than all other weighted decoding methods and matches the performance of methods that involve additional training. Furthermore, RAD achieves the lowest average maximum toxicity of any method. By adjusting the values used for weighted decoding, we can effectively balance toxicity and fluency. In our second experiment, we use RAD to steer the sentiment of text generated by GPT-2 Large. We evaluate the system on a variety of prompts and fine-tune RAD's reward model on millions of product and movie reviews. We measure the performance of RAD using the average positive rate, diversity, and fluency. Our results show that RAD achieves a better balance between fluency and positivity than any other weighted decoding method. It performs comparably to state-of-the-art methods that involve training. By adjusting the values used for weighted decoding, we can effectively balance fluency and alignment, allowing RAD to produce the best attribute scores. Section Summary. Weighted decoding in RAD involves re-weighting the probabilities of tokens based on their reward scores, which effectively rescales the probabilities of the top 7 tokens according to their relative difference in reward. RAD outperforms other methods in preventing toxic text generation and controlling sentiment, achieving a favorable trade-off between toxicity and fluency without sacrificing diversity, and producing the best attribute scores by tuning the scaling hyperparameter. Section: Scaling the language model. In all our previous experiments, we've been using GPT-2 Large as our primary language model, following the footsteps of earlier research. However, the latest language models have seen a significant increase in parameters, leading to a substantial improvement in performance. To put our RAD method to the test in more realistic scenarios, we decided to apply it to the cutting-edge llama models in the detoxification setting, using the same GPT-2 small reward model that we've been using. In our appendix, we've included a table, tab, scaling, that shows how RAD significantly reduces the toxicity of llama while maintaining its diversity and fluency. We've also included a table, tab, methods, that compares the computational costs of different methods for controlled text generation. While RAD and other similar weighted decoding methods do increase costs significantly when the language model and reward model are of similar size, the additional cost of using RAD is only about 3% when using Llama 65B as the language model and GPT-2 Small as the reward model. These findings confirm that RAD is an effective method for controlling text generation of state-of-the-art models, and it does so with only a minimal increase in computational overhead.